Hey guys, I am Aniket. Yeah, I'm a first year. I'm technically a first year PhD student here at Duke, working on quantum computing. But I've been with the same group as a master's student previously for the last 2 years. And yeah, I'm going to just be speaking a little bit about quantum computing. The idea is to start off at the very basic level, lay off kind of a foundation, and motivate the field in a sense, and then we can move towards some more complex, more interesting topics based on the group, of course. Let's take a couple of minutes if the rest of you could also introduce, so I know what you guys are up to, what you guys are interested in, and yeah, I guess Gurinder, you can start off, and then we can go around.
Sure. So, hi, I'm Giridhar. I'm completing my time at CFRCE probably in the next couple of months. But I've been studying quantum computing at CFRCE for about a year now. But before that, I was also involved with the physics and computer science groups.
Nice.
So hi, I'm Padmapriya, and I've been working on machine learning is what I got started off with, and after that went deeper into natural language processing. So that's what I've been working on mainly, and just started quantum computing a few months ago. And yeah, that's something I like to pursue too.
Sweet.
So hi, I'm Charu, and I started learning quantum computing a month back only, and I have joined for a PhD in PPISR for the same. So yeah, so I'm also interested, like if you can cover some how can we the applications of quantum computing in biology in some sense. I want to know how we can use it.
Yeah, absolutely. I'm going to be speaking about some applications today, but and I think I'm touching a little bit on the chemistry and biology ones. So, but I mean, if you are interested in those, we can have a further discussion on that as well. But oh yeah, I forgot to add. I was a student at CFRC, more or less before I started my undergrad here in the US. That is, I think I was a student there for about 4 years up until 2015 before I started my undergrad here. So, but yeah, so an ex student and still in touch with the community and with Dr. Ram and stuff. But yeah, so okay, I'm going to share my screen, get started, and of course, at any point, feel free to interrupt me with questions, comments, concerns. Don't hesitate at all. It's more of a discussion rather than like a one-way conversation. So please, yeah. All right. Just give me a thumbs up if you guys can see my screen.
Yep.
Fantastic. Okay. Great. Right. So I assume you guys can see this this page which says the agenda for today. So let me just run through what we're going to be doing real quick. The idea is I wanted to sort of divide this into like three major chunks. The first one was basics, and this would involve just going through what quantum computing is, the basic notion of a qubit, or what the operations on it, how it's different from a bit that you see in your regular computer, and also in terms of like what the catch is in quantum computing, right? Then the next thing I was going to discuss was like a quantum computing stack. When I say a stack, I mean like if you have a regular system like a laptop or a phone or something, a regular computer, there's a software stack that builds on top of each other, right? Starting from the low level hardware all the way up to the two languages. There's a similar thing going on in quantum computing, and I wanted to give a high level picture of what that is. And then lastly, I was going to speak about applications, some of the ones which are kind of hot and which are like have both near-term and long-term consequences. So it's going to it's basically a way for me to motivate the field. Like, okay, all this is cool, but what's the point of it? Why is this important? So so yeah, let me start off with the basic stuff itself. So I'm gonna start. So you guys can see me writing, right?
Yeah.
Fantastic. So in terms of quantum computing basics, let's start off with the regular computer first, right? In a regular computer, you know that all instructions are basically a binary stream. So what's a binary stream, right? It's a sequence of zeros and ones which convey some sort of instruction to your computer, where this is your computer, right? And so that's what a regular computer does. But the idea here is that each of your information unit can always be either a 0 or a 1, right? And how is this sort of implemented? The way this is implemented is it's basically it's a digital signal, right? This is 1, this is 0, this is 1, this is 0. So you have 2 zeros, you can have 2 ones. That's basically how it is. It's basically it can be either a 1 or a 0. And that's what a regular computer is. Your instruction is binary. It's binary because when you look at a software stack, your lowest level can understand only your TTL inputs. Those are then converted through assembly upwards towards the programming language. And this is how instruction execution happens on your regular system, right? So now here comes, so this unit of information in a regular system is what is termed as a bit. And this is a regular bit. So 1 or 0 is binary. It's always either of the two. It's an on-off signal. It's a Boolean. It's only in 2 states. Now, in quantum computing, we have what is known as a qubit. So all of you guys have, I'm sure because you guys have started learning about quantum computing, you know the basic idea of it. I'm just going to go over it once more. So what's a qubit? A qubit is basically just a quantum bit, right? And how is this different from a bit? So the idea of a qubit is that, let me just call the qubit we have as Q, right? So this Q can be not just in the state 0 or 1, but it also allows it to be in a spectrum somewhere between 0 and 1. You know, if you look at popular science articles, they sort of convey this message as, oh, it's 0 and 1 at the same time. That's kind of true, but not really. The idea is it can be a superposition between 0 and 1. So do you guys have like some exposure to quantum mechanics at all, or what's the room in terms of that?
We do.
Yeah, I had.
So since we're recording the session, if there's anything you'd like to explain a bit more, then go for it.
Sounds good. Okay. Yeah. So let me just speak about what this means, right? So when you have a quantum mechanical system, let's look at if you have any quantum mechanical system, the idea is you have, let me just this is like a harmonic oscillator. You have discrete energy states, state 0, state 1, state 2, and so on. The idea is you can be in state 0, you can be in state 1, but you also have this opportunity of being in a superimposed state where you are in sort of a state in between these, in a sense that and what a superimposed state means, that in this case, let's speaking about some particle, right? Let's say we're speaking about photons, right? What a superimposed state means that your system has some population of particles in state 0 and some population of particles in state 1, which basically means that your population is sort of both in 0 and 1, and the amount there in 0 and 1 is sort of determined by the amount of particles in there, and that sort of determines the probability of it being in the state 0 and state 1. So similarly, in a quantum mechanical system, in quantum computing, the idea of a qubit is you can be in state 0, you can be in state 1, and you can be in a superposition state, which basically means you can be in any state which sort of is a normalized combination of these two. What this means is you can be in a state, say 0 plus 1 over root 2. What does this mean? This means that you are 50% in state 0 and 50% in state 1, right? So this is a very theoretical sort of understanding of what a qubit is, but this is where the power of it comes from, right? So now, so like this is just one example. You can also be in a state wherein, you know, you are in 25% 0 and 75% 1. That's also a valid superposition, right? So the idea, and that's, I think, 1 by 2 0 plus root 3 over 2 1, if I'm not, yeah, root 3 over 2 1. Yeah, I think that's the decomposition of that. I think you can be 0 plus root 3 over 2 1. So this means that you have a 25% probability of being in the state 0, 75% probability of being in the state 1. So this is okay. This is a very theoretical sort of decomposition of what a qubit is, but this is also where the power of it comes from. And let me explain sort of why, right? So the idea is when you have a regular bit at any, so say you have a single bit, right? When you have a single bit, you have one unit of information. What I mean by that, what I mean by having one unit of information is that with a bit, say you have a single bit, you know it's in state 0 or 1, and that's deterministic. So let's say we're in state 0, right? So this basically is saying that you have one bit of information which is always 0. But now when you have a qubit, and because of course you can be in this, you can always be in like one or the other, like you can be in 0, you can be in 1, and in that case it's mimicking what a regular bit is, because you're just holding that information, right? But in a qubit, you can also be in a state where, like I mentioned, 0 plus 1 over root 2. So what this allows us to do is that when you're doing, when you're doing an operation on a bit on O, so let's say you have some operation O, right, that you're doing on this, yeah, so let's say you're doing some operation on this, let's call it, yeah, I don't know, yeah, I'm just looking for, I don't want to write O because it just looks like 0. Let me just call it X. So you're going to do some operation X on this, right? But this is still just giving you the ability to work on this single state, right? But the idea that when you have a qubit and you do an operation on this, again, let me just call it X. This is allowing you to do this operation on both your 0 and your 1 state, and not just a single unit of information, but allowing you to play with a combination of both your possible states. Because let's think of when you have a single unit, right? And if this unit has two options, right? This unit has option 0 and this unit has option 1, right? If you're looking at a problem that involves combinatorics, and if you're looking at a problem that involves you to have different permutations of stuff and you want to go through them, the biggest challenge is that this can always be one or the other. So it means you need to do something on this, you need to replicate and then do something on the other one, right? But the thing with the power that quantum computing gives you is now you have access to both of these at the same time. So you can work on them at the same time in the same operation, right? And the power of this really comes in when you go to higher numbers. So let me explain how. So when you have 2 bits, right? When you have 2 bits, so this was an example of just 1, right? So let's say when you have 2 bits, right? You can go in a classical bit. You can have, let's say you're starting off state 0, so you can have state 0 0, correct? But in a quantum bit, you can be, because you have, let's say your first bit is in 0 plus 1 over root 2, and your second one is also in state 0 plus 1 over root 2. This basically means that with just 2 qubits, you are encapsulating all 4 possible states available to you, because you can have 0 0, you can have 0 1, you can have 1 0, and you can have 1 1. And you see the power here, right? Because here with 2 bits in a regular computer, in a classical computer with 2 bits, you have access to only any one given state of the 4 possible states when you have 2 bits of information. But in a qubit, with just 2 qubits, you have access to all 4 states. So this means you're getting exponentially more processing power because you have exponentially more states and you have access to all possible states with that many bits of information to play with. And that is sort of, because, like, for example, you can extrapolate this further, right? In a regular bit, like in a classical bit, when you have 3 bits of information, let's say it can be either of these, right? It can be 0, 0, 0, 0, 0, 1, so on and so forth to 1, 1, 1. The key thing over here is that it's an OR. It's an OR. You can't have all of them, right? That's the key thing over here. But again, when you have a qubit, if your qubits are superpositions over here, just to keep the math simple, I'm making them equal superpositions, which means 50% probability. But as I mentioned, it can be any sort of probabilities that you want. Of course, they need to be normalized. That's the only condition. They have to be normalized because it's probabilities. They have to add up to 1. That's what that means. So yeah, so say, let's say you have 3 qubits, each of them in an equally superposition state. And so this, when you multiply out, you basically get the ability to have the access to all 9 possible states, which are all 8, sorry, my bad, to all 8 possible states which are available when you have 3 bits of information. So you see how this exponentially grows, right? When you have a single bit of information in a regular classical bit, it allowed you just one single state, either a 0 or a 1 to play with. But in a quantum bit, it gave you the power to execute on both the possible states at the same time. Similarly, when you had 2, you were able to do only 2. You were able to access just one of the 4 states possible. In a quantum bit, you had access to all 4 of those states. And as you move higher, this moves exponentially. So you see, like, this growth is kind of exponential, where this is the number of states available, and this is like n number of states, right? Where it kind of grows 2 to the n, where n is equal to number of qubits, right? So you see how this grows. Like with 4, you have 2 to the power 4, with 16, so on and so forth. And that's basically where this power of quantum computing comes from. This is why it's touted to be like, oh, this is going to make some things really fast and stuff. It basically is because you have access to all permutations of states with given n number of bits available in terms of bits of information, right? Are we clear so far? Any questions? Any comments?
Yep, I think we can go ahead.
Cool, yeah. So now that we have introduced what a qubit is and what it, Girija, I see your hand raised.
Yeah, sorry. I just wanted to ask a clarifying question.
Yeah.
It can definitely be something that's confusing in the beginning. So I just wanted to like ask it so you can clarify that.
Yeah.
The thing is, sort of, whenever you get this description of like you have access to, say, 8 times the amount of information as opposed to,
Yes.
right?
Yeah.
What ends up happening is, like, you start to think that you actually you actually have 8 bits of information as opposed to
Yes.
to 1. So
Mhm.
which is not exactly the case. So
Right.
how do you sort of explain the exponential speed up there?
Right, you're right. So the idea is, that's the catch, right? That's the catch. And I was going to get to this catch at a later point.
Okay, then no
Because
problem.
yeah, it's not all merry, because you don't really have access to 8 bits of information, because you still have 3 bits or 3 qubits. But because it's a quantum mechanical system, they're basically, each of them are storing sort of 2 states, and when you product them out, they give access to all 8 of them. But then there's a catch, and that catch, I'll come to the catch in a few minutes. Right.
Maybe here, just since Giriraj is asking clarifying questions, and these are, I think, FAQs that pop up when you're approaching the subject. So you mentioned how we implement classical bits. So it's a 0 or a 1. It's
Right.
voltage high, voltage low.
Yes.
That's like the basics of it. But when you say that we can have a superposition of bits, how is this physically implemented?
Sure. Yeah, I can speak a little bit about this. So the idea is that, again, that's actually a great question, actually, right? Okay, because as I mentioned, when you're thinking about implementations, I think that's the question that I think was this Padmapriya? Yeah. So in terms of implementations, right? Classically, it's just a digital signal, right? This is how it looks. That's what your bit is for that matter. But when it comes to qubit, when it comes to quantum, right? The idea is that your qubit is demonstrating quantum mechanical behavior, correct? Demonstrating quantum mechanical behavior. So that means the system that's implementing this needs to be a quantum mechanical system as well. So right now there are a bunch of sort of different implementations around the world based on who you talk to. Some people say this is the best, some people this is the best. It's a field in flux, but there are the two biggest sort of implementations. So the two biggest implementations are superconducting qubits and what's known as ion trap qubits. So again, bringing us back to the idea that the idea is it's a qubit, it's a quantum mechanical system, so it should be implemented by a physical system that demonstrates these quantum mechanical properties. So let me speak about the first one, right? Superconducting qubits. Let's call this A, call this B, right? So you go to A. You must have seen like up above, I drawn the diagram of like this simple harmonic oscillator, correct? And if you've done basic quantum mechanics, we know simple harmonic oscillator is the most basic sort of quantum mechanical system you have, and you still have these states. You have 0, you have 1, 2, etc. to n. So okay, one more on a side. I would ideally write these as 0, 1, etc. using the bracket notation, but I'm not sure what people's exposure has been to bracket notation in linear algebra, so I'm not going to use that this time. From next time around, I'll start using it, because I assume Giridhar is going to do probably going to cover things like this in his session a couple of weeks from now. Okay, so getting back to this. So the idea is a simple harmonic oscillator does give you access to sort of these 0 and 1 states, but it also has like 2, 3, 4, 5 to n based on sort of your potential value, correct? But the problem with a simple harmonic oscillator is that the energy separation is this energy separation here between your states. All of those are h bar omega, and they are equal to each other, right? Because to go from like the annihilation and destruction operators, if you know what those are, like if you have to go from state 0 to state 1, you need an energy excitation of h bar omega, and then similarly if you want to go down 1, you need energy release of h bar omega, right? And that's how a simple harmonic oscillator works. The reason we can't use a simple harmonic oscillator directly to create a qubit is because you have no idea of addressing a qubit, because you don't know whether you're in state 0, state 1, or state 2, because all of them are separated by the same energy level, right? So because for a qubit, you need to be able to excite it, or like put in a superposition state, or like sort of relax it, all of this, right? For this, you need to know how much energy to put in, so that way you know whether it's going to the next state or not, what state it is in, etc. And a simple harmonic oscillator, although in principle is a great, not just to an n-level system, the problem is because all of these are equal, that's an issue. So what superconducting qubit does is it uses this thing called a Josephson. So the idea is the way you can fix this is instead of having a simple harmonic oscillator, you can have an anharmonic oscillator. What an anharmonic oscillator does is your potential value looks something like this. I want to say instead of this. So this creates a division in sort of your levels. And what this does, let me just make this a little bigger actually. Yeah, so it creates something that looks like this instead of the typical thing that looks like this. And then when you have that, you can have sort of a division between your energies. So when you're 0, 1, 2, etc., these can be h bar omega 0, 1. This is h bar omega 1, 2, etc. So now sort of the frequencies to go from one state to other are different. And because they're different, you can now address and you can now know which state you are in and which state you want to go to, right? Ideally, you just care about this guy right here because a qubit is a two-level system, right? And the way superconducting qubits do this is they use something called a Josephson junction. A Josephson junction it's a circuit element which is typically denoted like this. This is what is known as a Josephson junction. And what this creates is it creates a so I mean I'm sure you guys know what capacitors are and resistors are, right? A capacitor and a resistor, like if you look at a capacitor and you look at so this is a capacitor, this is a resistor, and if you look at the IV curves of a capacitor and resistor, so this is I on this, V on this, it's a straight line. It's a linear voltage to current sort of deviation. A Josephson junction basically creates a non-linear curve here. So this basically makes non-linear differential capacitance. And when it does this, and when you put this in like a harmonic circuit, it creates an anharmonic oscillator in a sense. And this happens because Josephson junction is created using a superconducting material. When you cool it down, when you cool it low enough, it shows superconducting properties. And so there's quantum tunneling that happens, and because of quantum tunneling, it has a nonlinear sort of differential capacitance. Yeah, Giridhar, I see your hand raised.
Yeah, just a quick thing. Some of our students would be like sort of, they got into this from the computer science side. So,
right.
So if you get into any electrical stuff, it's probably better just like throw in, some of the general idea as much as required, not too much.
Oh, sounds good. Yeah. So yeah, I wasn't planning to cover this today, but because we had a question, I was just addressing it briefly because I know this also at a very surface level because I'm more on the computer science side of things as well. So I'm just going to give you as much high level as I can. But okay, let me just go through what this thing over here is, right? So a capacitor, resistor, yeah, I'm just explaining what this guy is over here. A capacitor and resistor are circuit elements. And what this curve over here is, if you had your resistor in a circuit with a voltage source and you were sort of my bad. You're just kind of measuring this. You're measuring the voltage, which is variable with the amplitude measurement. Yeah, with this amplitude. The graph that you get by plotting your amplitude, your current on one side, and your no, sorry, not amplitude. What am I saying? Amperes. It's an ammeter. It's basically measuring. Current here. So if you basically plot your current and your voltage, if you have a resistor and a capacitor, both of those give you a straight line. A capacitor is like if the mathematical relation between a capacitance and a resistance is just 1 over C equals 1 over R. Basically, it's so that IV curve will kind of be the other way around, because so this is the IV curve for a resistor. Because this is because they are reciprocals of each other, it's still linear, but it's a downward facing curve. And that's what this this little image that I drew over here means. And when you sort of have this in like this LC circuit, an LC circuit is a capacitor inductor circuit, and that sort of creates like this, like a harmonic oscillation. So LC circuit creates a typical harmonic oscillator in the electrical sense of things. But as I mentioned, the problem with the harmonic oscillator is your discrete energy levels are all separated by the same h bar omegas. You want to make it anharmonic. To make it anharmonic is why you introduce a Josephson junction, because as I have written in some very terrible handwriting here, this has a non-linear capacitance. And because it's non-linear, which then means it doesn't create a perfect harmonic oscillation, and because it's an anharmonic oscillation, it can act as a two-level system. The reason, and a Josephson junction, as I mentioned, so I'm just gonna call this for brevity just JJ. So JJ is made up of a superconducting material. Usually it's a aluminum oxide, aluminum as your sort of superconducting material. And the idea here is that the reason it needs to be superconducting, because when you cool it low enough, that's when you have quantum tunneling that happens. I don't want to get into quantum tunneling because that's a whole, I'm just giving you an idea of why it's nonlinear, because you have quantum tunneling that happens, and because of that, okay, let me track back. It's a superconducting material, which means when you cool it down, it demonstrates superconducting properties. Superconducting properties means you have Cooper pair boxes. This is a Cooper pair box, which basically means loose electrons. Your loose electrons can then tunnel through your potential barrier, which is quantum tunneling. And because you have quantum tunneling, this is why you have a differential capacitance, and which is why it creates an anharmonic oscillator. And that's one implementation of this one implementation of a qubit. If you want to understand a more practical way of superconducting qubits right now, just to be a little bit more practical, is being used by IBM, so IBM and Google primarily are using superconducting qubits for building their quantum computer. Now the next one, which is ion trap qubits, that's slightly simpler than this. You don't need to have that much knowledge of electronics here. An ion trap system, what it's doing, it's taking the most simple quantum mechanical system we know, which is an atom. It takes an atom. So you have a nucleus, then you have your things. This is neutral. So it takes an atom, it sort of excites this, so you get ions out of this. It sort of creates a two-level system. With ions. Ions, because it's a quantum mechanical particle, right? It's an ion. It's because it's within an atom, it already demonstrates quantum mechanical properties. So you basically use its natural two-level states as your two-level system. And the engineering challenges here is trapping this ion, like getting this atom, sort of exciting it. Exciting this, and then trapping it in a stable state, exciting to an ion, trapping in a stable state. These are like the main challenges that you sort of encounter. And in terms of companies working on this, it's I'm not sure if you guys have heard of this startup called IonQ. So IonQ does trapped ion quantum computing. Honeywell also does trapped ion quantum computing. So these are some of the big names here. There are, of course, a lot of other implementation, but I've just spoken about two of the big ones, right? So going on, I really want to get through. Okay, I mean, are there any questions on this? I mean, this is very high level. So, but if you do have some clarification, happy to answer questions.
I think we're good. Yeah, sorry, no need to interrupt your flow. We can go ahead.
That's fine, no worries. Okay, fantastic. Okay, so now before I spoke about this, I was speaking about, okay, so I introduced what a qubit is, and I think we've understood that, right? Now, going back, so now I'm going to speak a little bit about operations, right? Operations on qubits. Now, for this, we know, like, if you have a classical bit, let's say 0, you can do a NOT operation on this, right? A NOT of 0 equals 1. Similarly, you can have two qubits, and you can do an AND operation on them, and this gives you 0, so on and so forth, right? If I assume all of you guys have a computer science background, you know what I'm talking about, and this is just not gibberish. A NOT gate is sort of inverse. AND gate is, I assume, I mean, that's a different connotation, but so I assume you guys know what a NOT gate, AND gate, OR gate, XOR, all of that is. And so these are the operations you have. So these are all classical operations, right? So you can similarly do operations on a qubit. So just so I can differentiate between a classical bit and a qubit, I'm going to represent a qubit like this, which is 0, and this is 1, and your superimposed states can be 0 plus 1 over √2. This is the bracket notation, which is this, it's like a linear algebra concept. What this basically says is your 0 is actually a matrix which looks like 1, 0, and your 1 is also a matrix that looks like 0, 1, right? And your 0 plus 1 over √2 is this guy. The reason you need matrices to represent your bits is because, as I mentioned, they store more information that it looks like, and the best way to sort of represent this is through matrix linear algebra. I'm not going to go too much into this. I'm just basically consider this as a 0 qubit and this as a 1 qubit. Giridhar will speak a little bit more about all of the linear algebra formalism when he goes through this. But so you have operations on your qubits, and the 4 basic most primary operations are what are known as the polymatrices, right? So you have the polymatrices. You have 4 polymatrices, which is I, X, Y, and Z, right? And these are sort of your gates on your on a qubit. So what do these gates do? I is just identity. So when you have I on 0, this gives you 0. I on 1 just gives you 1. Plain, simple, easy, nothing much happening over here, right? The X operation is like your NOT gate, right? So when you do a X on 0, you get a 1. When you have an X on 1, you get a 0. Again, very similar to NOT, right? Now you have what's known as a Y gate. What does a Y gate mean? A Y gate basically means okay, I don't want to get into block sphere representation right now. I feel that'll be a good thing to get into in the next this thing. So okay, I just want to introduce these gates because we have about 10 minutes left. So I just want to introduce them and then move on, right? So a Y gate basically is a Y gate on qubit 0. What this does is, yeah, what it does is it inverts your state. So now you go from 0 to 1. But it also adds a phase of I, where I is the imaginary number root of -1. All right. So that's what the Y gate does on 0. The Y gate on 1 does, again, it does a similar thing wherein it inverts your state and puts a phase of -I. Okay. Why it does this, how it does this, that will require a little bit more of explanation, and I'll go through that the next time we're going through this, right? And then the next one, the last poly gate is the Z gate. A Z on 0, just if I'm not mistaken, Z on 0, yeah. So Z on 0 does nothing. So it's like the so a Z on O, a Z on 0 is equivalent to doing an I on 0, which basically means it does nothing on it. But a Z on 1 puts a -1 here, right? And that's what the Z gate does, is basically inverts the phase of your, it inverts the phase of your qubit for this guy. So these are the simple nice gates which basically do a single qubit transformation. But one of the most interesting ones, which really demonstrates the power of quantum computing, is what's known as the H gate, right? And this H here stands for Harmonic. The Harmonic gate. And this guy is really cool. Because what an H gate does is it can take you from a pure single level state. What an H gate does can takes you from single level state to a superimposed state. And so this is where you can finally get like the power of quantum computing really comes into place, because what this guy does is if you do a H on 0, this puts you in the 0 plus 1 over √2 stage. So it creates an equal superposition. Right? Likewise, a H on 1 creates a 0 minus 1 over √2 state. Both of which are equal superpositions. The only difference is the phase on 1. The phase is different. The phase on your 1 is different. It's a -1. All right? And so these are your basic operations. But okay, so you're like, okay, this quantum computing is all cool. You can do all these operations. You can go from a single state to a superimposed state. You have access to sort of all possible permutations of the bits of information that you have available, as we saw, like here and like here. But what's the catch? The catch is the quantum mechanics. And how's this a catch? Because I'm gonna explain this catch with the single qubit example. So if you are in the 0 plus 1 state, right? You're like, oh, this is really cool. Instead of having, because in a classical bit you had 0 or 1, right? And this is, give me a second. Let me just move this guy lower. That's good. Okay, yeah. So we have this. Yeah, so you have 0 or 1. This is the classical case. This is the quantum case. You're like, oh, instead of having just one or the other here, now we have access to both of these. The issue with quantum computing and with the qubit is that when you measure your state, so when you measure your state, you collapse it. What does this mean? What this means is, in a classical bit, when you have a 0, you measure it out, it's a 0. When you have a 1, you measure it out. I'm just going to call m as measure. That's just notation. And when you have 0, you measure it, it's 0. When you have 1, you measure it's 1. And this is classical, right? Similarly, when you in the quantum case, when you have 0 and you measure this, that's 0. When you have 1, when you measure this, you have 1. But when you have a superimposed state, which is 0 plus 1 over root 2, as I mentioned earlier, what this means is that you are 50% in state 0 or 50% in state 1, which means it's probabilistic, all right? And so when you measure this, this is non-deterministic. What does non-deterministic mean? It will not give you the same result every single time. Why does this happen? This happens because basic quantum mechanics, Schrodinger's cat, right? Schrodinger's cat is, you have a box, there's a cat here. I'm just going to draw the cat like a man because I do not draw a cat. There's a poisonous vial. The box is closed. We don't know if the cat is dead or alive. The cat may be dead, maybe alive. Before you open, it's dead and alive with 50% probability. Once you open, you know whether it's dead or alive. That's Schrodinger's cat. And that's exactly what happens here. Wherein both your states, a superposition state means it's in 0 and 1 over root 2, so it's a probabilistic state of being in both of, so you have, when you're doing executions, when you're doing your gate operations on them, you have the power to use the fact that you have access to all possible states with those number of bits of information. But when you measure it, you're collapsing it to give either 0 or 1. And this is the catch. So the idea is, when you're working with qubits, when you're doing a measurement, you want to make sure that the operations that you've done before it ensure that you're in a deterministic state when you're measuring. Because if you're not in a deterministic state when you're measuring, it's pointless. It's like tossing a coin. All the gates and the operation that you did in order to create this algorithm which solves the problem, if your output is not the same every time, or if the output needs to be deterministic, at least in the sense that, hey, if I get these outputs, it means this is the result, right? If that's not deterministic, there's no point of this, because it's like tossing a coin. It's chance. So then that's the catch with quantum. That's the catch in quantum computing, is that when you measure in a superposition state, it's a non-deterministic state. And why is that so? That's because it's a quantum mechanical system. So it brings us back to the very basics of a Schrodinger's cat. And when you measure it, once you look at the system, you're collapsing it. And so this is basically like a basic overview of what the field is, what it's doing. And I feel in the next, unless there are questions, I want to speak a little bit about the stack, the quantum computing stack, because I feel I've alluded to 2 parts of it already, and I feel I just want to get through that, if that's fine with people.
So I have one question.
Yeah, go for it. Yeah.
So you said in harmonic oscillator, let's say we have, let's not take an harmonic oscillator. So if we are in harmonic oscillator and we go from state 0 to state 1, so it's like adding energy h cross h bar omega.
Yes.
And so it's like applying x not gate, right? X, if I apply on 0 state, we go to 1.
Yes.
So so if I'm in an harmonic oscillator, how do I do that? Because the energy is not, it's not the same if I go to next level, right?
Oh, in an anharmonic one? You're talking about an anharmonic one?
Yeah, in
Okay,
in
like in this
harmonic
one.
oscillator, I can do not gate using X and go to next level. But in how do I do this in an harmonic oscillator?
Yeah, you do it. So the thing is, in a qubit, you just care about, in a qubit, you just care about this part of it, right? Let me use a different color for this. In a qubit, you just care about this part, correct? Because a qubit is a two-level system, you just care about 0 and 1, correct?
Right.
The issue with the harmonic oscillator is the energy to go from 0 to 1 is h bar omega, so is the energy to go from 1 to 2, so on and so forth. So you don't know where, like, sort of which state your system is in. In an anharmonic oscillator, you can still do a NOT gate by going from 0 to 1, but you give it energy h bar omega 0, 1, where omega 0, 1 is the frequency required to go from state 0 to state 1. And you know what this is because you designed the system, you designed the anharmonic oscillator, so you know what your energy differences are between your levels. So if you want to do a NOT gate to go from 0 to 1, you supply this energy. If you want to do a NOT gate to go from 1 to 0, you sort of release that energy.
So basically, your X gate flips the spin in X direction, right? That's what it does.
Yeah, it does a rotation about the x-axis, correct.
Yeah. So we can decide the energy, like we can decide the frequency. I'm asking. I don't know this. Um, so is it not like it's always H cross omega, or we can decide
So in
what
this case,
omega
it
does?
is not always h bar omega, right? It's h bar omega 0, 1. The reason this is important is because if your state was in state 1, because this is an anharmonic oscillator, you're going to have some populations like across. You're going to have some populations here, some populations here, some populations here. But the transition, if you supply exactly this energy, will only affect these two states because that's the energy associated with their difference.
Okay, right.
Yeah.
Oh, okay.
And so
follow up to this question. Yeah, go on. If you were
yeah,
explaining.
go for it. Yeah.
Yeah. So what I see here is there are two states, and because it's two-level quantum system, all we care about is state 0 and state 1.
Yeah.
But you have an n-level quantum system. Is that practical? How would you implement it? Would you use the same gates to manipulate the system?
So there is this broad concept of a qubit, which is it's a D-level system. That's what a qubit, like instead of qubit, it's a qubit. There is a concept of that, but it's not the idea of it is, okay, why restrict yourself to 2 levels? You can go higher. But then that makes it a lot more complicated in terms of what you can do with it, and also sort of the trade-off with having access to n levels. How much does that really help? Because you must understand that the more levels you're adding, sort of the more sort of engineering challenges also exist, both in terms of doing gates and also in terms of error correction, because it's a quantum mechanical system, which means there's a lot of errors. So it is a field which is very new, a lot of research being done, but not as mainstream yet. I mean, even this is not that mainstream, but it still is not even close to being where this is. But that idea does exist of what's called a qubit, and a qubit is a 3-level 0, 1, 2, and a qubit is generalizing it to like D levels.
Got it.
Yeah. But it's there's in term, because the idea is also you want it to be this like a computing system, right? So a 2-level system sort of solves that problem very nicely and like extrapolates well as well. So yes, I was just going to go through the stack really quick, just to understand, just to like give you guys a picture of what's going on in the field at the high level, right? So I'm going to start bottom. I'm just going to go bottom up, correct? So I'm going to use some colors here. So the lowest level is this here is hardware, right? When I say hardware, I'm talking about this can be superconducting, this can be ion traps, this can be any other implementation that exists out there. So it's very physics, a little bit of chem, electrical engineering based, right? You're building the system. That's the hardware side of it. Then you have this layer above it. Right? What does this layer do? This layer basically is the electronics. Let me be consistent in. So the electronics, why do you need electronics? Because you need to control this hardware. This hardware is controlled via an FPGA board, which has wires and chips that control the different components of your hardware, and that's why you need electronics, right? This is very EE, so still a little bit of computer engineering. That's where this field is, right? Above that, you have the I think this is good. Yeah. Above this, you have this is the microarchitecture level, right? What is microarchitecture? You need software that controls electronics, right? This is Verilog, this is your instruction set architecture, all of that stuff. So it's basically, and so this is written here, right? So right above that is, let's go with this color. Right above that is sorry, yeah, that's the one I was looking for. Yeah. Yeah, so right above this is sort of compiler slash control software, right? What is compiler slash control software is because you're getting some instructions from a high level like this. You want those to be parsed, compiled, and compiled such that they can speak to your electronics, that those electronics can speak to your microarchitecture, microarchitecture can speak to your electronics, electronics can control your hardware. So this compiler control software layer, and okay, so that's what a compiler is, or what a control software also is. It kind of, they're very closely related in the sense you wouldn't expect everyone to know microarchitecture level code because that's very assembly, very log kind of work, right? Control software sort of puts another layer of abstraction above it in a sense, and speaks and like talks very close to the compiler and like the microarchitecture. It's like a bridge between a compiler and a microarchitecture to give you like that one other level of abstraction. And this is where we're getting into real computer science territory. Still a little bit of computer engineering because you need to know the microarchitecture level below it a little bit. About this comes programming languages. Examples of this, I'm pretty sure you guys must have heard. There's Qiskit. There is Q#, which is, so Qiskit is IBM, Q# is Microsoft, and there's also Circ, which is Google. Right? And above the programming language layer is where you have, this color is very similar. Let me just go to another one. I guess that's good.
I guess maybe it's a question with the scope for another time, but technically these programming languages are are sort of more libraries and extensions as of now, right there?
It depends. It depends, right? So you can use Qiskit as there are two ways. You can use things like Qiskit and Q# directly as a language, but you can also use them as a library inside Python.
Okay.
Or like
There is a direct language component.
there is also a direct language. Yes. Yeah, so the layer above it is algorithms, and this is like the theory stuff, right? This is basically things like creating algorithms to solve problems. This has like, say, Shorus. You have your Deutsch Josha, DJ's Deutsch Josha here. You have your Bernstein Vazirani. These are all algorithms trying to solve problems. So all of this is very much in like the math and theoretical computer science space. So you are creating algorithms, you have error correction. I'll get into error correction a little bit next time, but that's basically another big problem and a big bottleneck that quantum computing faces. So you have error correction, which is like your Steam codes, your surface codes, etc., which is basically, again, a very theoretical thing. And so this is sort of what your QC stack looks like. So the bit that I touched upon right now is very much in the theory space. So that this is most of what I spoke about today, your gates, your operations, and all of that. I did speak a little bit about this part because this is the hardware, the superconducting stuff, the ion trap stuff that's like very physics, very pure engineering kind of work. The area that I primarily work on is kind of here. Oh, sorry. Yeah. So the area that I primarily work on is somewhere here. More on the computer science, computer engineering side of things, wherein we sort of create a bridge between, we write control software to control like our experiments in the lab, like our quantum computing implementations in the lab. We also try to abstract it to higher levels of programming languages, so a little bit of compiler work, a little bit of microarchitecture work. But yeah, so that's the general space where I work. So yeah, this was just like, I just wanted to give you guys like a big picture idea of where, so the field has people working everywhere, right? As like most of the big companies, they have efforts across the stack. Like if you look at Google, Microsoft, IBM, Amazon recently, bunch of startups, they work across the stack. They have theorists who are working on algorithms and error correction. They have programming languages of their own, which means they're compilers of their own, and the stack below it, they're working on their own software, they're working on their own hardware implementations, like I mentioned, IBM, Google doing superconducting stuff. So they work on across the stack. Also, like going back to Charu's question, your applications is also a part of this guy here. Applications, it means you're trying to use algorithms to solve useful problems. So those also sort of fall on this layer. So now you have some startups, so your startups in this industry, and those sort of, some of them focus on like parts of the stack. Here's some people just working on this, some people just working on hardware, some people just providing compiling and software solutions, some people working on just applications, some people working on just error correction. So as far as opportunities, they are available across the stack and super specialized as well. So yeah, just a quick summary of what the field is doing and like a big picture idea. But I guess that's all. That covers a bit of what I wanted to go over today.
Perfect. If you want, you can sort of give like, I don't know, 30-second, 40-second thing on applications, but I'm good with the
I feel I want to spend a little bit more time on that. I feel I wouldn't be able to do it enough justice with like a couple of minutes. Yeah.
Yeah, sure. Perfect.
So we can just pick up from there next time and go forward.
Cool. That's a great.
Yeah, I'll have this sort of converted into PDF and sent to Giridhar, and then he can share it with people if they're interested. Yeah.
Thank you.